Hi guys, it's Professor Stevens again. Following up from the previous video, I just did a lesson on the probability of at least one, and I covered a lot of concepts there that all tie together, so it's a good idea to watch that before watching this one. And this is about constructing a discrete probability distribution, and probability distributions are introduced in Chapter 5 and in Chapter 6, but Chapter 5 is about discrete probability distributions in which you have data that can be counted, and Chapter 6 is continuous probability distributions, which are usually data that can be measured with some sort of instrument like a ruler or a measuring cup, something like that. So things that can be counted, such as chicken eggs, people, years of age, things that have nothing in between the values, are discrete. And that's what Chapter 5 is about. 5.1 is about probability distributions in general, and in section 5.2 we get into binomial distributions. I'm going to refer back to this example we did where we had a collection of values. Right here is where it was introduced, and we were looking at the probability of having a success in each trial. And if we boiled it down to saying, well, B, the letter B would be a success, then we had a probability of success, P equals 1 over 10, or 0.1 as a decimal. And Q, the probability of failure, not having the letter B in a single trial, would be 9 out of 10, or 0.9. So we're going to use that as a basis and kind of pick up with something we were doing before, which was looking at the tree diagram to figure out all the different ways that you could have a certain outcome. And the tree diagram is where you start off with saying, okay, let's do n equals 4 trials, where you're going to select a letter from those 10 values. And in each trial, you can have success or failure on the first trial, then success or failure on the second trial, and so on. And then you could list and count all your ways of getting those 4 trials, picking 4 letters out of the collection of 10. And then you could look at the probability of a certain number of successes, in each trial. So our sample space would have been, all successes, then maybe 1 success, and that can happen a number of ways, but you could figure out what all of those should be by following the paths down to the little buds here. So SSSS, and then SS. The next one, if you were following the tree diagram, would actually be SSSF, and so on. And then you would figure out all the different ways. Once you had that, you should figure out that you have 16 simple outcomes in your sample space. And another way of figuring that out that's shorter than listing and counting is to look at the 4 trials and say, okay, I have either a success or failure in each possible for each trial. Either I'm going to get the letter B or I'm not going to get the letter B. So that was 2 times 2 times 2 times 2. Total of 16 simple outcomes. Right? But looking at the probability of each individual outcome is not as simple as saying 1 out of 16, because in this example we had the probability of success 1 out of 10, or 0.1, and the probability of failure 9 out of 10 rather, or 0.9. So because they're not equally likely outcomes, we can't just say that the probability of SSSS is not 1 out of 16 like it would be if we had a 50-50 chance of success and failure, like in the case of boy or girl, yes or no, and so on. But we've got at least a basis for understanding how we could know all the different ways that you could fill up those 4 spaces. There's 16 different ways, but then you have to realize that this isn't true. Actually, for that one particular outcome, you would be doing the multiplication rule, where you did 0.1 on the first trial, probability of success is 0.1 on the first trial, then 0.1 again, then 0.1, then 0.1. So just for that one outcome, that would be your probability. And then likewise, if we looked at the second outcome here, the probability of SSSF would be 0.1 times 0.1 times 0.1 times 0.9. Okay, so that's just enough information for me to take you over to the Excel spreadsheet and show you how to build, I'm going to start it from scratch here, how to build a probability distribution. So let's let x be our random variable, and it's discrete, where x equals the number of successes in n trials, and n would be the number of trials. So for this one, we would have n equals 4. And then we would also want to know our probability of success and our probability of failure. P is 0.1 in this case, and Q is always 1 minus P. Okay, well, before we actually put this into a probability distribution, we're going to do each number of successes that are possible in 4 trials, which you could have no successes, 1 success, 2 successes, 3 successes, or 4 successes. And then let's look at how the different outcomes that are favorable for each one of those. So doing our tree diagram, we could come up with SSSS, where there, or excuse me, that would be FFFF, where there are no successes. Or if there were 4 successes, that would be SSSS. We could also look at 1 success, so like SSFF, but then that success could also be the second trial, or the third trial, or the last. And likewise, if we had 3 successes, that would be 1 failure. That could be, the failure could be in the first place, or the second place, or the third place, or the last place. And then for 2 successes, that could be the first 2 trials are successes, or the last 2, or maybe the successes are on the outside, or maybe they're on the inside, or maybe they're alternating success, failure, or the other way around, failure, success, failure, success. And so the number of favorable outcomes would be 1, 4, 6, 4, 1, symmetric. Now, there's a formula we learned about in the accounting section, NCR, which was for combinations, and we'll do it here, but we'll do NCX. So N would be 4, and we're going to use the combinations combine function here. So that would be 4 trials and 0 successes. You could just type in a 0, but I'm using a reference here. And then here it would be, again, combine 4 trials with 1 success. And you can actually copy that formula down if my mouse will work properly. There we go. And so you can see how it's kind of cool when you understand what the combinations formula does for you and how to do it in Excel. It's very easy for you to come up with all the different ways that you can have a certain outcome in this scenario. And this is actually binomial. This is not just a discrete random variable, but it is a binomial random variable. The requirements of binomial random variables are that you have a fixed number of trials. So like here we have 4 trials. Okay. You have only 2 outcomes which you can boil down to success or failure. And you have, I mean, that part of it right there is what makes it binomial. There's only two possible ways. And then you also need independent trials, or independent events. And then you also need a constant p in each trial. So we had that here because the probability of success for each of our spaces we were trying to fill was always 0.1. And it was always 0.1 because we were allowing repetition. So this is binomial, and there is actually a formula for binomial distributions, which I'm going to build up to. But I'm just going to, before I get there, I'm going to explain how you get the probability of each one of these events. And then when I show you the next part, it'll be more interesting. So let's look at these particular outcomes and then the probability of each outcome. So with FFFF, that was going to be P 0.1 on the first trial times 0.1 on the second trial, and on the third, and on the fourth. So another way of saying that is 0.1 to the power of 4. Okay, on the next number of successes, we could have SFFF, and that would be 0.1 on the first trial, success, then failure on the second trial, failure on the third trial, and failure on the fourth trial. Or another way of saying that could be 0.1 to the power of 1 success times 0.9 to the power of 3 failures. And I guess I'll do it like this: 0.1 times 0.1 times 0.1 times 0.1, and show that that's the same thing as 0.1 to the power of 4. And this was 0.1 times 0.9 times 0.9 times 0.9, which is the same thing, and I need an equals in front of that, which is the same thing as 0.1 to the power of 1 times 0.9 to the power of 3. But that's for, you know, if I'm looking at a number of successes, X, and that was for 0 successes, and this is for 1 success. But that's only in the first position, but remember we came up with 4 different ways to have exactly 1 success. So again, with 1 success, you could also have FSFF, which would be 0.9 times 0.1 times 0.9 times 0.9. Okay, and notice that's the same thing as above. And that's because with multiplication, remember 2 times 6 is equal to 6 times 2 is equal to 12. Whether you do 2 times 6 equals 12 or 6 times 2 equals 12, they're commutative, meaning that you can do multiplication in any order. So the fact that I have 0.9 in here 3 times and 0.1 in there once, it's the same thing as right here above it, right? So, and I can show you that again here. For having the success be in the third trial, what would that be? That would be 0.9 times 0.9 for the first 2 trials, then 0.1 for the success in the third trial, and 0.9 in the last trial. So you're going to see that this happens for all 4 of my different possible ways of getting a single, exactly 1 success in 4 trials. Right now it's 0.9 times 0.9 times 0.9 times 0.1. Right, so for all of those, now I have 4 of these. And if I'm going to add those probabilities together to give me the probability of 1 success, because this is 1 success, or this is 1 success, or this, or this. So the word or is implied here, so the probability of exactly 1 success is actually adding together all 4 of those scenarios, or all 4 of those cases. So this is where I'm going to stop doing that because it's repetitive, and I think I've made the point clearly enough And what I'm going to do instead is show you how to make this into a probability distribution. So the probability distribution is where you say, here's my x, and here's my probability of x in this column. And so I could have 0 successes, 1, 2, 3, or 4. And then for this one, it's going to be one way to get 0 successes times the probability of success to the power of no successes times the probability of failure to the power of all 4 failures. Then in the next one, it would be 4 ways to get exactly 1 success times the probability of success for that 1 success to the power of 1 times 0.9 the probability of failure to the power of 3. The other 3 will be failures. Then 6 times 0.1 for 2 successes times 0.9 for 2 successes. Then 4 times 4 ways to get exactly 3 successes. So 4 times 0.1 probability of success to 3 successes times 0.9 to 1 failure. And then finally, one way to get all successes, all 4 successes, and no failures. And when I add this together, it should be 1 because I've covered all the possibilities. And there you have it. That is a probability distribution, a discrete probability distribution, meaning that my values of x are from a counting process. Okay, there's nothing in between 0 and 1. There's nothing in between 1 and 2. And I can count these. 0, 1, 2, 3. I'm counting successes. Alright, so, and that happens to also be binomial, as I explained. So it's specifically a binomial discrete probability distribution. So if it's not discrete, you can't do it like this. You need a curve. And so we see those in Chapter 6, but Chapter 5 is all about discrete probability distributions. And 5.2 narrows it down to binomials as a special type. Let's look at another type of discrete random variable. Let's look at, let x be the number of, let's set it up. Let's say we're rolling a die, like a regular 6-sided die, and let x be the number on top of the die when it lands. So then x can be 0, or not 0 this time, x can be 1. There's no 0 side of a die. 2, 3, 4, 5, 6. So notice we're not counting the number of successes here, but it is still discrete. The values of my random variable are countable, right? The dots on the sides of the die are countable. And then the probability of x is 1 out of 6 for each one of these, right? Well, it's going to turn it into a date. Let's undo that. Do the equal sign. So it's the same for all of these. And this is kind of like not the type of thing you really need to do a probability distribution for. It's kind of like extra work for no reason, but just to show you how the sum here will be 1, obviously, because I've got 6 sides, all with a probability of 1 out of 6, assuming that it's a fair die and not one that's loaded. But it might be more interesting if we said, let x be the number of times 6 is rolled out of 5 rolls. Okay, now this became binomial because you could either have 0 6s rolled, 1 6 rolled, 2, 3, 4, or 5, because there's 5 rolls. And then all these are going to be different. And so then you would be back to trying to figure out how many ways there were to do each. So if we try to find the possible outcomes, you could have a 6 on the first roll, or if you had no 6s, then you would have a failure 5 times, right? And if you had one success, a 6 was rolled just on one of the 5 rolls, then you would have SFFF, FS, FFF, FFS, FF, and so on. But you don't have to figure that out, because remember, we figured out how to use NCX to figure out the number of ways. So what I'm going to do instead is I'm going to say how many ways using NCX, and I'm just going to do it like combine 5 trials and X successes, and then copy that down. And if my mouse will cooperate, there we go. And then to figure out the probability of success in each trial, it'll be the number of ways times the probability of success. Well, the probability of success, well, 6, right? Rolling a 6, there's a 1 out of 6 chance on any, I'll write it like this, 1 out of 6. On any given roll of getting, there's a 1 in 6 chance of having a success. 1 in 6 chance of rolling a 6. Times, and that would be to the power of 0 because that's with no successes. Then times the probability of failure, which would be 5 sides out of 6 that don't have a 6 on them. And that would be to the power of all 5 rolls. And then here I can do 5 ways to get the probability of success to the power of 1 times the probability of failure to the power of the remaining 4 rolls, and so on. And it's interesting that those are the same. But what I'm going to do next is I'm going to show you how to make this even easier to copy the formula down. So what we're going to do is we're going to make space to put the number of trials, the probability of success, and the probability of failure. If we're doing 5 rolls, the probability of success is 1 out of 6. The probability of failure in each roll is 5 out of 6. Or you could just say equals 1 minus P. Alright, and then for here, we're going to do number of ways times the probability P, and I want to F4 that, because if I F4 it like this and put the dollar signs in there, so I'm hitting F4 to make that happen, but you can also type the dollar signs. That reference will not move. While the B7 reference is relative, when I pull the formula down, that will change to B8 and then B9 and so on. The B4 will not change. I want to use the same probability of success every time. And then I want that to be to the power of the number of successes right here. And I do want that to be relative. I want that to get pulled down when I copy the formula. Then I'm going to do the probability of failure, F4 that, so I stay the same every time for that. And then to the power of the remaining, so this is n minus n, F4 minus zero. So the remainder of the number of successes. See? Same as before. Now we're just going to copy that down so far. And now when I add this up, if I did it right, it should give me 1 F4. Okay, so that's a binomial distribution, and this is using the binomial formula, which you learn about in 5.2. So 5.2 with the binomial distribution, we learn the probability of x successes is NCX times the probability of success to the power of x successes times q to n minus x. That's what we've been doing in the Excel spreadsheet here. That's actually what we did. And just to show you, I'm going to verify it. With Excel has its own little binom distribution. I wrote binom PDF up there. Not what I wanted. There we go. It says it wants number of successes. That's this. It wants the number of trials. That's this. And I want to always refer to the same value for that. And is it cumulative? No. 0 for no. Because I only want exact probability of exactly 0 successes. Oops. What did I miss? Number S, trials, probability of success. Yeah, before I say whether it's cumulative or not, I have to tell it the probability of success in each trial, and that I want to be the same every time. And it is working just the same way that I programmed it with the formula. And then what's interesting too is if I add, I put binomes, let me fix this up here. In the graphing calculator, it's binom PDF, but in this it's binom.distribution in Excel. So let me just fix that. But then I also want to show you that if you want to do cumulative, that's actually useful, because if you take, let's just simplify this table a little bit. I'm just trying to set something up that's a little easier for us to look at, less convoluted. Alright, now over here, I'm going to do P of x less than or equal to a certain value. And so if I were to do it by hand, I'd start off with this. Less than or equal to 0 is just that. Less than or equal to 0 would be 1, the sum of the probability of 1 or 0. That would be x equal to less than 1 or fewer successes. And then 2 or fewer successes would be the sum of these. And then 3 or fewer successes would be the sum of these. And you get the picture, right? Now, look what happens if I use binom.distribution cumulative equals 1, meaning yes for cumulative. So I'm going to do the same thing I did before. Binom.distribution, number of successes, number of trials is 5. Probability of success in each trial, right there, F4. And then cumulative, this time I'm going to say yes for true. And so far it looks the same as before, but if I copy that down, you're going to see how it matches the sums. Except for this last one. Wait, something happened here. I guess when I copied it, it didn't copy right. I didn't notice that. Let me fix this. So this one would be the sum of all of these. And this one would be the sum of all of them. Yeah, now they match, right? So that's a good trick to know. So what I ask you to do on the test typically is to make a binomial distribution, or you show me that you know how to calculate it yourself using this formula with the aid of Excel, like we did here. And then how to verify it using the binom.distribution formula. And then also how to do the cumulative probabilities like this using the sum function. And then to verify them using the binom.distribution cumulative function. So those are things that I do look for you to do on the test. Then once you've got your distribution established, you can use it to answer questions. Like I can tell you right now, by looking just at, let's focus on this right here. By looking at this, I can answer a lot of questions. So what kind of questions can I answer? Let's see, I can answer, what is the probability of exactly 2 successes? The answer would be right here. What is the probability that x is less than or equal to 2? That would be right here, cumulative probability. What is the probability that x is strictly greater than 2? Well, that would be equal to the sum of these, strictly greater than 2. Or another way to get that is to do 1 minus the probability that it's less than or equal to 2. See? So this is a really great way for me to see if you know how to read this table. So not only did we construct a distribution, we constructed a binomial distribution using formulas and functions in Excel, and then we learned how to read the table and use it to answer questions. So that's a lot of useful information. There is an EMP assignment that involves using all these skills that I've just shown you. And hopefully this clears up quite a bit that you're going to be encountering in 5.1 and in 5.2. And then there is probably one more thing I could tell you about this, how to use this distribution to your advantage. And that is coming up with your mean, your variance, and your standard deviation. But I won't be able to go into all of that here. I think it would make the video too long, so I will start another video on that. And that will be called Parameters of Probability Distributions. All right, see you on the other side. Let me see if I can figure out a way to get out of here now.